Rocks in space. What are asteroids? Asteroids are rocky bodies that orbit the Sun. They are much smaller than planets. We find most asteroids in a region called the asteroid belt. This belt lies between Mars and Jupiter. Early asteroid discoveries were important. They gave us clues about the formation of our solar system. These space rocks come in different sizes. Some are as small as pebbles, others are hundreds of miles wide. Asteroids are leftovers from the early solar system. They are like time capsules from billions of years ago. By studying them, we can learn about the conditions when planets were forming. A German astronomer's lucky find, discovering Juno. In 1804, a German astronomer named Carl Ludwig Harding made an exciting discovery. He was looking at the stars and noticed something unusual. It was a faint object moving against the background stars. Harding realized he had found a new celestial body. It was an asteroid, later named 3 Juno. Juno was the third asteroid ever discovered. It followed Ceres and Pallas. These early discoveries sparked great interest in studying asteroids. Harding's discovery was important. It helped astronomers realize that there were many more objects in the solar system than previously thought. Sizing up Juno dimensions and mass. Juno is a fairly large asteroid. It has an irregular shape, but on average, it's about 145 miles or 234 kilometers in diameter. That's about the size of the state of Connecticut. To put it another way, if Juno were a sphere, you could fit about 14 million of them inside the Earth. Juno's mass is estimated to be around 2 times 10 to the 19th kilograms. While that sounds enormous, it's actually less than 1% the mass of our Moon. Despite its size, Juno is still dwarfed by the giant planets in our solar system. It serves as a reminder of the vast range of sizes among celestial objects. A closer look, Juno's lumpy shape and composition. Juno isn't a perfect sphere like a planet. Unlike the smooth, round planets we are familiar with, Juno has a unique and irregular shape. Instead, it has a more irregular, lumpy shape. This uneven form is quite different from the spherical shapes of planets and moons. Imagine a potato tumbling through space. That's kind of what Juno looks like. Its surface is full of bumps and craters, giving it a rugged appearance. Scientists believe Juno's irregular shape is due to impacts from other asteroids over billions of years. These collisions have played a significant role in shaping its current form. These collisions have left their mark on Juno's surface. Each impact has created craters and indentations, adding to its lumpy appearance. Juno is classified as an S-type asteroid. This classification helps scientists understand its composition and origin. This means it's composed mainly of rocky materials, including silicates, which are common in the solar system, like the minerals that make up much of Earth's crust. These silicate minerals are essential components of many rocky bodies in space, and some metals, primarily iron and nickel. These metals are also found in the cores of planets and are crucial for understanding planetary formation. Unlike some asteroids that contain ice, Juno appears to be relatively dry. This lack of ice suggests it formed in a warmer region of the solar system. Its composition provides clues about the conditions in the early solar system when it formed. By studying Juno, scientists can learn more about the environment and processes that existed billions of years ago. Section 5. A celestial dance, Juno's orbit and rotation. Juno orbits the Sun in the asteroid belt. It takes about 4.36 years for Juno to complete one full orbit around the Sun. Its orbit isn't perfectly circular, it's slightly elliptical, meaning Juno's distance from the Sun varies throughout its orbit. Juno also spins on its axis. It takes about 7.2 hours for Juno to complete one rotation. That means a day on Juno is much shorter than a day on Earth. Juno's axis of rotation is tilted at a significant angle. This means it experiences seasons, just like Earth does, but they're much shorter due to its faster orbit. Section 6. Shining light on Juno. What its surface tells us. Astronomers can learn a lot about an asteroid by studying the light it reflects. Juno's surface is quite reflective for an asteroid. This high reflectivity suggests that Juno's surface is covered in metallic materials. These materials are likely remnants from the early solar system. By analyzing the spectrum of light reflected from Juno, scientists can identify the minerals and elements present on its surface. These observations help us understand the conditions in the early solar system. They provide clues about the building blocks of planets. Section 7. A relic of the past, Juno's significance. Juno is a fascinating object for astronomers. It's a relic from the early solar system. Its composition and structure provide a glimpse into a time when planets were forming. By studying Juno, we can learn about the processes that led to the formation of our solar system. Juno's relatively large size makes it one of the most massive asteroids in the main asteroid belt. This suggests that it may have once been a larger body that experienced collisions. These collisions could have stripped away outer layers, leaving behind the Juno we see today. Studying these remnants helps us understand the violent history of the asteroid belt. Section 8. Unlocking the secrets of the solar system. Juno is like a puzzle piece in our understanding of the solar system's formation. By studying its composition, orbit, and physical characteristics, we gain valuable insights into the processes that shaped our cosmic neighborhood. The presence of metals on Juno's surface tells us about the distribution of elements in the early solar system. Its irregular shape and heavily cratered surface reveal a history of collisions and impacts, providing clues about the dynamic environment of the asteroid belt. Section 9. Future exploration, missions to Juno and beyond. This section delves into the exciting possibilities of exploring Juno and other celestial bodies in our solar system. While we've learned a lot about Juno from Earth-based observations, sending a spacecraft to study it up close would provide a wealth of new information. The detailed data collected from such a mission could revolutionize our understanding of this asteroid. A dedicated mission to Juno could map its surface in high resolution, revealing intricate details of its terrain that are impossible to see from Earth. It could analyze its composition in detail, identifying the various minerals and elements that make up the asteroid. The mission could also search for signs of water ice, which is a key resource for future space exploration and could support long-term missions. Discovering water ice on Juno could pave the way for resource utilization, making it a valuable target for future missions. Such a mission would not only deepen our understanding of Juno itself, but also provide crucial insights into the broader context of asteroid formation and evolution. The data gathered would be invaluable for scientists. The data collected could help us refine our models of the early solar system, offering a clearer picture of its history and development. By studying Juno, we can better understand the processes that led to the formation of planets, including our own. This knowledge is essential for piecing together the story of our solar system's origins and evolution. Section 10. The never-ending quest, continued study of asteroids. The exploration and study of these celestial bodies have fascinated scientists and astronomers for centuries. The study of asteroids like Juno is an ongoing endeavor. These rocky remnants from the early solar system hold clues to the formation and evolution of our planetary neighborhood. As technology advances, we develop new tools and techniques to observe and analyze these celestial objects. Modern telescopes and space observation technology have revolutionized our ability to gather data and understand the complexities of asteroids. Future telescopes, both on Earth and in space, will allow us to study Juno and other asteroids in even greater detail, revealing new secrets about their composition, history, and potential resources. These advancements will enable us to capture high-resolution images and conduct in-depth analyses that were previously unimaginable. The knowledge we gain from studying asteroids is not purely academic. It has the potential to revolutionize various fields, including space mining and resource utilization. By analyzing asteroid samples, scientists can uncover valuable materials that could support future space missions and even benefit industries on Earth. It has practical implications for protecting our planet from potential asteroid impacts. Understanding the trajectories and compositions of these objects allows us to develop effective planetary defense strategies. By understanding these objects better, we can develop strategies to mitigate risks and ensure the safety of our planet for future generations. International cooperation and collaboration in space missions are crucial to achieving these goals. The quest to understand asteroids like Juno is a journey of discovery that will continue to inspire and amaze us for years to come. Each new finding brings us closer to unraveling the mysteries of our solar system and ignites the curiosity and imagination of future generations of scientists and explorers.